So thank you again to Ash. I'm actually the next speaker, so I'm going to set up. In the meantime, I see there's some people standing in the back. If you'd prefer to stand, you're obviously welcome to, but there are some seats available if you'd like to sit. So just while I get my laptop set up, if you're interested in finding a seat, please feel free. Especially like sort of in this row right here, there's like 3 or 4 seats. Oh, and my thing is showing up. So that's great. Looking good. So I am the last speaker before lunch, so I'm going to ask Michael to be like really aggressive, controlling us getting to go to lunch. So also, if I go over time, just please feel like free to start walking out. I'll only cry a little bit. All right. So again, thanks everybody for attending the mini. So I'm going to be talking about one of the projects that I work on at work. Just like Ash, I work for the AWS Quantum Computing Group, but not for the Center for Quantum Computing. Rather, I'm a scientist on the Amazon Braket team, and I'm going to be talking about our Julia SDK for Braket today. If you attended a Cajun meetup earlier in the winter of this year, some of this will look familiar, but if not, I'll try and give an introduction to what Braket is, why we're using Julia for it, and then how folks can get involved. So just like a quick intro to me. So I've been a Julia contributor working on quantum stuff since January 2015. Occasionally have given talks about it at JuliaCon, and have been at Braket since 2020, and before that was at Flatiron, so shout out to all the Flatiron folks here. And I have totally destroyed my brain with both quantum and Julia-related content. So if there's anything that's unclear, please feel free to just stick up your hand in the middle of the talk and ask, and I will be happy to address your question. So as I mentioned, I work on Amazon Braket, which is part of the overall quantum computing group, but distinct from the Center for Quantum Computing. So to quickly give you the sort of 2-second introduction, Amazon Braket is a cloud service available through AWS, Amazon Web Services, for accessing both quantum devices and then also simulating them. So it's kind of a one-stop shop for a variety of quantum technologies you can use to both sort of simulate what your circuit might do on the device and then also actually run on the real hardware to understand how it's performing. So our pitch for folks who are interested in using quantum technology, which as probably most of us know is still pretty embryonic, is that we let you build, test, run, and analyze so you can easily build circuits, test them with simulators, and then run them on real hardware, and then finally use a bunch of other technology available through AWS to analyze the results. Yay. So during this talk, we're going to be almost entirely focusing on the left column here, build, because we're talking about the SDK. But if you're interested in finding out more about the other aspects of this or want to go into more depth, I'm definitely happy to talk about it as a sidebar later on during either lunch or the BOF or something like that. So please feel free to reach out if that's interesting to you. And I'll just give like a very high-level overview of how this sort of whole service is organized as part of AWS. So on the left here, we've got users queue public, so a bunch of happy sort of cartoon users. They're working either through their managed Jupyter Pluto notebook, or maybe they're just running stuff on their laptop, probably like most of us do day to day, or maybe they're using the console on the AWS web page. They send some tasks. So like I want to run this circuit to the Braket service that's hosted on AWS. Let's say they run on a simulator or like a real device. Having done that, then maybe they go actually run on quantum hardware, and the pipelining for that is handled by us. And then they're able to integrate with a bunch of other Amazon services, for example, so that they can monitor how their task is doing or make sure if they're trying to do a quantum algorithm run on data that's sensitive, that's handled appropriately, things like that. But again, we're going to be almost entirely focusing on the left side of this diagram because that's the part that we've written in Julia. OK. So again, just another quick pitch of we do have a bunch of different hardware technologies available that you're able to use through the SDK that is in Julia, as I've shown. And in particular, I really want to shout out to QEra here on the left, who are the analog Hamiltonian simulation device. They are a sponsor of JuliaCon, and they have a table downstairs in the main hall. And they also have a really great Julia package I'll be mentioning again, Braket.jl. So if you're interested in that, definitely talk to them and also to us. This is kind of an area that we're working on together. So if you have any thoughts about what could be more useful or features we should support, please come talk to us. We also support now on Q's new trap-down device, Aria. We have Rigetti's Aspen M3 and OQC's Lucy, and there's always more devices coming to the service. So if you're interested in testing out these sort of new technologies, come check us out. And then we also have a bunch of simulators that we allow folks to use. This is something that I work on more directly. We have simulators that run sort of locally, we would say. These are run like on your hardware that you control, so that would be like your laptop, or if you have a cluster you're running, or we have ones that are managed by us, where all the compute happens behind the scenes in the cloud. I'll just show the slide, and you can read more about these on the documentation for the service if you're interested. And we can think of when we're interacting with a service like this, there's kind of two levels to the SDK, as John sort of mentioned earlier when discussing Qiskit. There's kind of high-level and low-level components. So higher-level components might be something like a convenient API to create circuits and apply noise to them, and then say, I want to measure this kind of result. Like, I want to measure an expectation value, or I want to measure a state vector if I'm running in a simulator. And then we also might have higher level constructs like building an analog Hamiltonian simulation program, or maybe if we really want to get fancy, building microwave pulse gates, since we know better how we want to do that necessarily than the default option. And then other constructs would be, when we run the circuit, we get results. Okay, I want to use error correction or error mitigation through some API for that, like if I want to use MIDIC. And finally, there's things like querying the device, learning facts about it. So an example of that would be like, what's the topology of Rigetti's device? Like which gates are connected to which gates? And what are the current fidelities that they're reporting for those gates? And also, especially very important on hardware is cost tracking. So if I want to run like 100 circuits of size whatever with this many shots, how much is that going to cost me? But then behind the scenes, there's kind of lower level components. So there's the raw results, so just literally the shot bit strings that are reported to like the mitigation software. There's the actual circuit IR or program IR that is sent to the service when it interacts with the device that the sort of convenient circuit builder then translates to when it submits things. And then there's behind the scenes constructs for actually kind of controlling what the service does. So we can think of these convenience routines that allow us to like quickly build up circuits, and then much lower level calls that let us do things like submit HTTP post requests to the actual devices and like check device statuses. So our goal with the package I'm about to introduce, Braket.jl, was to have a Julia interface for both of these levels, because some folks want to be able to write their own circuits with their own language, and we don't necessarily want to be able to force everybody into kind of our dialect or our paradigm. So we have a complete rewrite of the Braket Python SDK in Julia, both sort of the high-level components I just discussed, and then also the lower-level components that let you directly submit, for example, IR in our specific IR language or OpenChasm to the device. So our goal here is to allow people to use almost every aspect of the service that's available through the Python SDK without actually having to use Python if they don't want to. So nearly every feature is available without needing to install any Python packages. The one situation this is not true in right now is if you want to use one of Amazon's pre-written local simulators. Those are currently only in Python. More on that at the end of this talk. But everything else you can do in pure Julia. Both, this allows us to avoid having to install either Python call, which is a wonderful package, or PyJulia. And it also frees us from kind of having to use the Python language for everything, like in the sense of sort of the Python architecture, the Python way of thinking about things. Python's a great language, but we're at JuliaCon. We like Julia. Julia has its advantages as well. Sorry. That Ash had discussed. Let me get some water here before I start just dying up here, even more than I already am. And we want to offer the Julia quantum community a first-class experience to either build on what we've chosen as a paradigm for creating circuits and interacting with them, or building their own custom solutions that fit what they want to do better. Okay, hopefully that's better. So we support multiple computing paradigms that are available on the service. We'll talk about gate-based circuits first, because this is probably the one that most people are familiar with. So we support all the gates and noise operations that are available in Python. We have a large variety of gates and almost all sort of Markov noise that is available to run on our noise simulators. And you can attach all of the result types that are supported, like expectation values, variance, amplitude, all that good stuff. And we support running in an exact, you could say shots equals 0 or shots equals infinity, depending on the language you like. Of course, this is only in simulators, or more probabilistic, so shots greater than 0, what the device actually does, kind of runtime paradigm. So that lets you, if you're running on a simulator, model what the device actually does, or these raw results and do the processing for you. So for example, it can figure out what the expectation value is if you ask for 100 shots. And we're currently looking for help, as I'll mention again at the end, at integrating with more sophisticated kind of post-processing, so things like error mitigation, error correction, observable estimation, things like that. And another thing that we're able to do, which of course the Python SDK is also able to do, is run these sort of simulations concurrently, especially on the managed devices. And as I mentioned, QEra is using Julia as well with their blockade package that lets you build analog Hamiltonian simulations for their device. So in the interest of time, and also not to steal their thunder, I'm not going to go in depth into how analog Hamiltonian simulation works. So stay tuned for Roger's talk later. Or if you want to know more about that, talk to him or John from QEra, or go see the QEra sponsor table. Also, if Pedro's here, yes, talk to Pedro. So they're the analog Hamiltonian simulation experts. But it allows us to program a device with controllable atom geometry in 2D, and we're able to control the waveform pulses that are used to actually run simulations on these Rydberg systems. And we have an integration with Braket.jl that allows you to construct these kind of simulations in their high-performance simulator and then translate directly to running on the device from QEra that's available on the Braket service. So you can do the entire sort of setup, and analysis, testing, and running entirely in Julia, which is pretty cool to me. And then finally, we are able to run so-called dedicated jobs, which you can think of kind of as like end-to-end experiments. So this is a feature we offer called hybrid jobs. Effectively, what it is you have a Docker container and some script that you want to run. So an example of when you might want to do this would be, let's say you want to run QAOA on one of the devices we offer, or you want to compare how two different devices run the same QAOA algorithm. So with jobs, you can spin up a Docker container with whatever software you want and then just point it at some quantum hardware. It gets priority access to the hardware while you're running. And at the end, it'll report all of the training information. So if you want to get some graphs to put in your paper or something like that, it's able to do this for you. And again, this is entirely doable in Julia. Setting up a job like this that's all in Julia is a little complicated. So if anybody wants to see a demo of how to do this, I'm happy to show one. But again, in the interest of time, I don't want to take up too much time being like, check out my Docker file. But it's actually not as complicated as it might seem. And one thing that's really nice about this, especially for people who are more expert developers, is you can embed and use your own simulators or software. So for example, if you're a huge iTensor fan, we don't natively support iTensor, but that's fine. You can easily build it into a Julia Docker image and just run stuff, and then compare it with what the actual device is doing. So to kind of sum up, I want to just mention a couple opportunities for people who want to contribute, and also maybe discuss a few common areas of interest, both for us, like people coming from the quantum group at Amazon, but then the wider quantum community here. So before I do that, I'm going to take another sip of water. Cool. So as I mentioned, QEra has this really great package, Braket.jl, that allows you to simulate up to 50 atoms on their neutral atom device, and which is able to submit tasks to their QPU pretty seamlessly using Braket.jl. So we have an ongoing integration with that software, but there's definitely a lot of opportunity for people to contribute more to that. So if folks are interested, for example, in replicating results that have been published on various analog Hamiltonian simulators, using the software, that's definitely something we can work on supporting, especially if there's features that you need that are not currently present. And we also currently have a plugin that exists to support Yao.jl. So of course, probably everybody here who's vaguely familiar with Quantum knows about Roger's awesome Yao package. So this is kind of, you might call it like the quantum flux. It allows you to do all kinds of differential programming for quantum computing, and we now have an integration with it. So if you currently have like a script or a workflow that you've been running with Yao, you should now be able to run it on real hardware if that's something that interests you. So I think that's pretty cool. This plugin was developed as part of Penny Lane's Q-Hack this year by some very enterprising students. So there's definitely a lot of opportunity to make that plugin perhaps like a more featured, add tests to it, add demos. So again, if that's something that interests you, come talk to us during the hackathon. And the fact that we implemented sort of all levels of our SDK in Julia means that creating integrations with something like Zygote or, Enzyme or Flux is really straightforward. And it means that you, for example, do not have to interact with Python objects if you don't want to. And similarly, if you want to build your own circuit representation, as long as you can teach your circuit representation how to become OpenChasm 3, then you can use all of the features I've discussed about running stuff on real hardware, running it on simulators, without ever having to deal with the choices that we made about what we want circuits to look like. And so for this reason, it's really easy to write like a plugin or connector for whatever quantum software you want to use, and make that available as either a local simulator that somebody runs on their own hardware or as kind of a higher level framework on top of this. And our goal is to make things kind of purposely low level and then let people who have a specific application in mind build stuff on top of it. And we want to enable people in Julia to have a first-class experience when they do that. And so I should mention that we are looking for contributors. There's lots of opportunities for people to add things if they'd like. I think one of the big sort of low-hanging fruits is adding support for local simulators. For example, if there were a tensor network software you wanted to use to run MPS-based circuit simulations, it's pretty straightforward to add a sort of pass-through support for that. Adding integration with the Yao ecosystem, as I mentioned, and then higher-level templates for algorithms like QAOA, VQE, QAA. All of these, of course, obeying the iron law that any quantum algorithm has to have a Q in the name. I finally escaped tensor network world where every algorithm also has to be 4 letters long. So maybe someday we'll escape the Qs. Another area that would also be great to have folks adding support for would be measurement approximation techniques. So by that I mean like classical shadows, Povum-based techniques, other very jargony things. And then finally, one of the other areas that we currently don't have full-featured support compared with Python is support for pulse control, like creating waveforms, frames, things like that. So if that's something that interests you, again, come talk to us, especially at the hackathon. And we have a README with lots of open contribution ideas and issues if you want to find out more. And we're also very excited when people submit feature requests or bug reports. So if you come look at the package and you're like, this sucks, I want you to support this, please just let us know. And it's great to add stuff that people would actually like to use. And if you're not yet a quantum expert, that's fine. There are options for you too. And by that I don't mean like, oh, if you don't have a PhD, you're not an expert. It's more like if you're sort of, we would say like interested in quantum, but you haven't been studying it for a while, you don't know that much about it, that definitely does not mean you don't have anything to contribute. So please, both if you have thoughts for our package, but in general with the Quantum Mini, let us know if there's something you'd like to work on, or if you don't know what to work on, but just want something to be offered to you, come let us know. And then I would also be remiss if I didn't mention that we have credits available, both for academic research and open source development. So for academic researchers, including PhD students independent of your advisor, you can acquire credits to run on any of the AWS services, including the quantum hardware. So if you want to do something like that, come talk to us. Ash or I can help you out. We can hook you up with credits to be able to run on quantum hardware if you have a research idea that you want to implement. Or if you're a PI and you want to do the same thing, again, just come talk to us. We can work with you on getting that set up. And we also have open source credits available for general open source development. That's handled by a different team, but we're definitely available to connect you with them and hopefully advocate. And then we also work with Unitary Fund to provide microgrants for open source contributors. So if you're not familiar with Unitary Fund, it's an organization that gives people these microgrants, like $500, $1,000, to implement a feature in a variety of quantum softwares. And we've also worked with them to do mentorship for people who are sort of joining the quantum software developer community. So if that's something that you're interested in, again, please come talk to us. And then finally, we have internships next summer for people who are PhD students. So this summer, we're all full up because it's the middle of summer. But especially if you are a sort of senior in your graduation PhD student, you're interested in getting an internship in the quantum industry, we do have opportunities opening up for next year. So come find any of us and we can give you some information about that. Or if you're a PI who has a student who might be interested, we're also available to talk to people in that situation. And so just to kind of sum up, we're going to be at the Saturday hackathon. And if you're interested in finding contribution opportunities in the wider quantum software world, we'd definitely be happy to point you towards something. So come find us. There'll probably be like a whole little sort of scrum of quantum people. I would say like come find where the nerds are, but this is JuliaCon, so we're all going to be there. And then just to kind of summarize everything, so we have a new Julia SDK for the Braket service, and we want people to try it out and use it and see if it's useful for them, or if not, then that also teaches us something interesting. We're interested in finding out what are Julia users and developers wanting to learn about quantum technology as a whole, especially because we know that there's so many people at JuliaCon who are currently doing really cutting edge research in the areas we talked about when we were doing the very informal survey at the start of this. So like folks in mathematics, condensed matter, quantum information. So we want to understand what tooling you need to be able to do the research you want to do using the actual hardware that's available. And then we also want to know what you would need to make it easier to build and experiment the stuff that you want to test. And then the big open question for me is, what are the common areas of interest and needs? So the very obvious gimme answer is we need an OpenQASM 3 package. Ash is obviously there agreeing. I've had this discussion with several people. So leaving aside the very obvious answer of we need an OpenQASM package in Julia, what are areas that different groups can work together on to enable the whole community to do things better? And what are the current pain points in Julia, like a feature that's not available or something Base is doing that's really frustrating that prevents us as a community from building the software we want to build, from being able to study the questions we want to study? What from like the groups making hardware available is not present that people in academia or as researchers in industry want to use? What do they need that's not currently available, or what's available but the experience of using it is really painful? I think that's like for us the real question that's going to enable us to make the Julia quantum community like very strong coming out of the gate and able to compete with certain other languages that are very common in the quantum community. So with that, I actually did not use all my time, so we should have lots of time left for questions. Thanks again for attending. I'm Katharine. I'm on Twitter, GitHub with 2 accounts now, also on Mastodon, and I'm out of Blue Sky Code, so sorry about that. And if you have any questions that you want to ask, we have plenty of time, or you can go to lunch early. So thanks again, and yeah. Does anybody have any questions? Okay. I'm going to give you the microphone. Oh, yeah.
I'll try to project not that much. So I was wondering on the pulse optimization side, or like the sending pulses side, you said there's a lot of work to be done there. I was curious, like, what is it look like on the measurement side? Like, you send a pulse, are you just getting back a fidelity, or can you say anything to that?
Yeah, so currently our measurement format is entirely like you send, let's say, like an OpenQASM 3 program, which may include open pulse sequences, and then you just get back some bit strings. And you can do with those bit strings whatever you like, right? So if you are able to plug in those bit strings to something like MIDIC or some other framework for doing like error mitigation, then you're ready to roll. But we currently basically like offer you like, here's the you know, in the Z bases, the bits you measured, and you can choose to do whatever you want with that information. But if you don't know how to make sense of it, then that's very sad. And we do also provide like some transforms, for example, if you want to like change the measurement basis, we're able to support stuff like that. But currently it's like very low level, which is why I mentioned sort of measurement protocols or like measurement optimization techniques is definitely kind of an area where there's a lot of opportunity to make things better. For example, like we currently don't support POVMs at all. POVMs. Sorry, this is another very annoying jargon. If you don't know what a POVM is, it's a positive operator value measurement. And it's a way that you can measure or approximate various observables, especially things that have lots of polystrings with fewer measurements. That's like a pretty inaccurate 2-second summary. But if you're interested and search it on Google, you'll learn a lot about what POVMs are or aren't. Yeah, so I guess to actually answer the question you asked, there's like very bare bones support for measurements right now. So if somebody's interested in adding more, like compute the fidelity of this gate between these 2 qubits or something as a high-level routine, that would be very welcome for us. Yes, that would also be extremely cool to have, and it's not currently, I mean, you can implement it, but it's not currently provided. Cool. Other questions? Yes, you do.
I was just wondering about, you mentioned open chasm support, because I think I even talked with you about this at IQ Hack, and we needed it at Zapata, and there was nothing available. And I just had to hack something for the limited use we had. But is there nobody even started working on that yet?
I mean, I don't have access to like the interior minds of everybody in the room even, so I don't want to say like nobody has started doing this, because probably somebody has. I can say there's definitely like internally in our quantum group people who are working on this, but if this would be like generally available, I don't know. So I think it would be something like, if we can definitely discuss this further during the Birds of Feather session later, which is like more of a general discussion for those who don't know. Sorry, I should have defined that before. If we're, you know, if this is something we as a community want to work on, even starting during the hackathon, for example, that might be something very interesting for everybody to align on, or at least like people who are working as package developers. Other questions? Oh, no. Yeah, go for it.
So for the noise models that you mentioned, are these noise models fitted to the hardware systems that you guys specifically have access to?
So we don't currently offer like pre-built noise models. So for those who've used IBM Qiskit, you probably have seen that IBM offers like a specific pre-built noise model for like their Lagos device, which is great. Because we offer a bunch of different hardware providers, and because that hardware is theirs and not ours, we allow you the flexibility to kind of build up a hardware model on your own, and then you can run it. So for example, if you wanted to do some sort of like reinforcement learning to kind of learn a reasonable noise model for the device, that's something that you would be able to do with some work. But we don't currently offer like, here's our noise model that we imagine is true for this device, especially because, probably as many of you know, the noise model the noise that the device experiences can drift over time. So that's also something that would be great if people want to build like, here's our community estimation of what the noise model for this device should be. Or if you want to get a little more sophisticated, the device reports these fidelities between these 2 qubits, like 1Q and 2Q fidelities. So based on that, we think the noise model should be blah, 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 blah. But that's, again, not currently pre-built or provided by us.
Have you been thinking about, or is there anything in there about compilation or circuit transformation? You must have to do layout, for instance, to go to hardware from like a, all-to-all connectivity.
So currently, the support that the Julia SDK has for like compilation or controlling how that's done is pretty bare bones. So for example, we provide like sort of verbatim sections that tells the device, like if you submit to Rigetti, for example, like even if 2 qubits on Rigetti's device are not directly connected and you submit a CNOT between them, you can effectively force their device to not try and compile that CNOT. Now that may not be a very advisable thing to do, but it's possible to do if you want to. But besides that, we don't offer as many compilation, I guess, tools or controls yet as perhaps other providers might. So if someone wants to develop like a pass-through to either talk to them, like for example, Rigetti, Quill is Rigetti's compiler, yes, or some of the IBM compilers, that would also be something that would be a very cool project. Yeah, that usually happens after you submit your OpenCASM to the service. So we do support some native, like for example, on IonQ's device, we support the Molmer-Sorensen gate, which I probably mangled the pronunciation of. I'm very sorry if anybody knows how to pronounce that correctly. But we are definitely looking forward or hoping that folks will build like more sophisticated compiler techniques on top. And I am out of time, so if folks want to discuss more, why don't we do that at lunch? We'll be back here at 2 p.m. I wouldn't necessarily leave your stuff in here because this room isn't like guarded or locked or anything. But yeah, let's go get some lunch. There's food trucks downstairs. And again, thanks for your attention.